Welcome. I'm glad you're here. I'm glad I'm here. Yeah. So I'll let people filter in, I guess. I don't know. A little bit. Before I get started, I guess my name is Carmen. I work on, if anyone's familiar with Travis CI, it's a hosted continuous integration service, and I'm on the build infrastructure engineering team there based out of New York. And I thank you for coming to this talk. Okay. So I have a confession to make. I've come here from the year 1983. No, really, I time traveled. And I'd like to thank some of the people that helped me acclimate myself to this early 21st century. And Jerome Petazzoni is the first, but didn't make it into the PDF. Yeah, you will for the posterity. He's right there. Dave Cheney, Alan Donovan, Steve Francia, and my whole team at Travis CI. So back to 1983. Imagine that you are my fellow software engineers from the year 1983, and you happened upon a time machine, and you traveled to 2017. You get a glimpse of an opportunity to see the future of computers and the exponential impact that they've had on society. You'll maybe start to look for ideas to take back with you, and maybe you can be the person to make the next Lugal. Ever the curious person, you dive into everything that you can about what's happened over the last 35 years with programming, from where you left it in 1983 until today. So you soak in everything about the current programming languages and software engineering practices. And you'll get to see some of the predictions that you've had about hardware were confirmed. And you'll be in wonder of some of the things that are still going strong and in wide use today, some 40-odd years later. You'll get to see this fairly new idea of object orientation, started by Smalltalk a few years before 1983, and then see it integrated with C and have it be named C++. And then you get to witness how that really takes off. And you'll see things getting added and iterated and polished and wrapped and super wrapped. And you'll see the evolution of this thing that we call a stack, or in 2017, you'll see how and why we call it turtles all the way down. And you'll see that computer coding has grown big time. There's this thing called the cloud. And that's just really other people's computers. But all this growth is because source code is now largely available and free on the internet. The internet came in 1990 for my fellow 1983ers. And TCP/IP was also finalized in 1983. And yet, for all I just mentioned, a vague but exciting internet, by the way. That's the original paper by Tim Berners-Lee and the handwritten note by some of his supervisors. And there's the TCP/IP, proposal including HTTP protocol. And yet, for all I've mentioned, which was just but a fraction of what's happened in 35 years, you'll see that software engineering as a profession, languages, practices, it's still largely unstandardized. And it's bustling, and it's ever growing, and it's moving like a bazaar. There was even this book about it. I don't know if I want to read it, though. So what you'll see without exception are all these ideas coming from previous ideas. I mentioned Bell Labs here because Bell Labs was really de rigueur for some of the innovations in 1980, and those are still in use today. They're also the combination and maturation of old ideas, and they're born from the very same people. So even though you'll see this growth of ideas and languages, you'll also find a curious anomaly, a language called Go. I give you this 1983 thought exercise partly because that's often a comment that I hear about Go, that it is a language often criticized as being stuck in the 1980s, that Go has taken all the last 3+ decades of language design evolution and seems to just ignore it. So I want to talk about some of the things that people first criticize about Go before I talk about the design decisions. As listed here in this lovely curated GitHub, case Go is not good, you get the same complaints over and over again. Too simple, lack of syntactic sugar, no generics, bad dependency management, stuck in the 70s or the 80s, bad error handling, no unused imports, too opinionated, too verbose, no ternary operator, no macros or templates. Okay, I'm out of breath. But I said that all in one breath. And most of the people who haven't really understood Go ask themselves the points, or the title of my talk, which is why. So I'm going to say, why, Go, why? Why and where other languages have evolved, Go looks like it has not. It's a curious anomaly. Why would a language even consider itself a 21st century programming language with things like this? So this was really my question. Why it's moving in sort of like this opposite direction. And thus this talk is a product of my quest to find out the why of Go. And I'd like to share that journey. After celebrating 5 years since Go's inception in 2012, one of the creators, Rob Pike, said, Go programming language was conceived as an answer to some of the problems we are seeing developing software infrastructure at Google. It was created and conceived at Google. The computing landscape today is almost unrelated to the environment in which the languages being used, mostly C++, Java, and Python, had been created. The problems introduced by multi-core processors, networked systems, massive computation clusters, and the web programming model were being worked around rather than addressed head-on. Moreover, the scale has changed. Today's servers comprised tens of millions of lines of code and are worked on by hundreds or even thousands of programmers and are updated literally every day. To make matters worse, build time has stretched to many minutes, even hours, on large compilation clusters. I could probably read that entire article and it's from here and make that my talk, but I do want to visit some of these statements and delve into them more fully, chronologically and thematically. Chronologically, I want to start from Go's creation and move forward and backward from this point to understand what was present at the turn of the century and move forward and backward. And with this timeline, I'd also like to organize things into 3 broader themes: software and languages and associated tooling, hardware, multi-core processors and threads and green threads. We're going to talk all about that. And then context, which means events, industry, social, historical. Because one of the things I asked myself to answer this why of Go was recognizing time, place, context, and people. Because humans write languages and code, and they don't do it in a vacuum. So let's explore this. People. Ooh, I'm from 1980, so that's pixelated 8-bit. Robert Griesemer, Rob Pike, and Ken Thompson. It was conceived at late 2007 at Google by these 3 people. And this, if you know who these 3 people are, this is a long legacy. I want you to think about, for your programming career, whether that's 2 years or 10 years or coming on 20 years, think about in the past anything that you've built or done and wish maybe you could go back knowing what you know now. Because between these three, they have built or have had a hand in much of what we personally use every day. I couldn't even fit it on this timeline because yeah. So Ken Thompson wrote at Bell Labs Unix, what would be Unix in the 1960s, and then on like a summer off, he went to go write BSD. He also then helped Dennis Ritchie write C, and then he and Rob Pike at Bell Labs would write UTF-8. There's more as well. This is the legacy. It's kind of hard to see, but this is the legacy of starting from the PDP-7 operating system, the first version of Unix and beyond, right? And that is Ken Thompson and his legacy. So to continue, we also have Rob Pike, who wrote Plan 9, which will take a prominent place in Go, the operating system. And we have Robert Griesemer, who worked on and was one of the primary architects of the Hotspot Jvm. And that's important to know right now because I'm going to talk about that and the relevance of that in a little bit later. But I think of Go as being a product of these things that were continuances out of these bodies of work of these three men. And perhaps a product, what I think Go is like maybe a product that fixes the things that maybe haunted them, right? A product that remedies the shortcomings that they could only see, but see in hindsight. And what I'm noticing is that, or at least have an inkling of, is that they're not interested in revolution. They're interested in simplicity. So I've talked about people and who's. Let's talk about the actual technical limitations around 2007. And then what Go, talk about historical context around the decade prior to that. And then talk about what Go did in its approach to the language design to try and see if they can solve it. So the things that are 21st century about Go, a language often accused from coming from 1980s, are these things in my opinion. So concurrency, distributed systems, garbage collection, memory, but especially memory locality, and readability. So I'm going to talk about each one of these and try to give you a little bit of context and history. First, massive concurrency. Efficient support for massively concurrent programs. So 10 to the 6th green threads, which in Go parlance is called Go routines. That's quite manageable for Go. But why green threads? And why massive concurrency? Of all the problems out there, why did these three individuals choose that? And in order to understand why the creators of Go chose green threads as one of the first-class features of the language, I had to understand concurrency primitives. So that means that I understand threads and events, and finally green threads at the beginning of the 21st century. So green threads, really quick before I get started on this try-line, for those of you who don't know, green threads are the user-level threads. So they're scheduled as an ordinary user-level process and not by the kernel. And green thread memory is allocated from the heap rather than the stack created for it by the OS. So in Go, they're known as Go routines. And do I have it? Oh, I have it here. So there's Go in 2007, and then we have C++ at Google around the mid-early aughts. Getting efficient concurrency at scale was important, especially for servers. Google's experience with C++ in 2005 was awful. They couldn't afford one thread per connection, and so they had to use these callbacks and event dispatchers, and it was leading to this horribly inverted style of programming. And with Go routines, you could just write a sequence of statements in the logical order. And so there's a lot of history behind the Go routines that's more nuanced than simply just threads are bad and Go routines are good. So 15 years ago, we had the C10K challenge, when basically threads were terribly expensive. And once ePOL, which is a scalable I/O event notification, and KQ, which is the BSD equivalent, they came around 2004 and 2000 respectively. They replaced their older predecessors of poll and select. And so a lot of the effort shifted from how to write programs in this event callback environment. And you had these papers, which I'll put up in the context, like CETA and Java NIO and Python Twisted and Apache Mina, but none of those really caught on. They had lots of little groups and people committed to doing whatever it took to master that technology and learn to think in whatever the async framework required. But a few other things happened around that time to dim the newfound promise of events. Threads got better. Hardware got better. Now there was some actual competition. So operating system people had something to aim at. Previously, threads had been faster than processes, but now the incentive was wrong. But now they had a clear goal, and it turned out that there was a lot of low-hanging fruit to pick. So hardware got better. Yeah, here it is. Unless you had access to huge servers, big iron like the Sun E450s or the E3500s, you didn't actually have more than one processor, right? And the market for workstation CPUs, not just in the Intel realm, but MIPS and SPARC, was single socket up until about 2005. And although you can get dual socket Pentium 2 and Pentium 3 boards, most people were focused on the gigahertz, on the clock game, right? But once we have the Pentium 4 with that hyper-threading in 2000, P4, and the Core 2 with dual core on a socket in, I think it was 2006, the game changed, and especially changed on the server. So in 2007, you could buy 8 cores on a dual socket chassis. So now you see the trends in CPU cores and clock speed and transistors here in the software improvements. And I put it all the way up until the blue dot ago. So the very bottom black is number of cores, and we're starting to see multi-cores. And then you sort of see some other power consumption in watts, the clocks, which is the frequency, the single-threaded performance, and then last, of course, is Moore's law of the transistors. So you had multi-processing, many CPUs, many tasks at the same time. And we had thread advocates. The thread advocates won back all the ground that they lost to events. And they didn't necessarily overtake them, but the playing field was a bit more even. And now that servers could easily have 4 or 8 cores for a few grand, all of a sudden the process model got a second lease on life. So there's Ruby with Mongrel and Python Unicorn, Python, the multiprocessing, and everyone was back in the game because for moderate workloads, it turned out that you could just throw cores at the problem and you got, at least on the web tier, near linear scaling, at least for a time. But I think the creators of Go saw the writing on the wall for threads and hardware even in 2007. So you see here, we're plateauing on modern hardware. And Go routines, they realized, even in 2007, that Go routines and grethreads were really going to be the best possible solution. But why? I keep going back to the why. Why do Go routines give us the best of both worlds between threads and events? And to me, I think that the answer comes from taking this wider perspective than just what generates the best graph in a benchmark. Because focusing on just the absolute point in time result ignores 100% of the software engineering that went into that benchmark. And I'll talk about that in a little bit. But what do I mean by that? Okay, so let's go off on a little bit on the event side. Some programs that benchmark really well using events, Nginx is a good example, right? It's this a whole event loop plus state machine model, which works well because HTTP is a very structured protocol. So like you read the request line, you read headers, read body, write status line, write headers, write body. And all of the configuration is declarative in Nginx. So for this path, matching this pattern, apply this transformation. But you notice that nobody writes their application logic inside Nginx. They always put it in front of their app. Why? Why isn't Nginx an app server like Tomcat or JBoss? The Nginx model, while manageable for small groups of dedicated developers, it's just too nerdy for the wider group of developers. Imagine being told, yeah, Ruby is too slow. You need to rewrite your program for Nginx. But first you have to download a C compiler, and then you have to build your own state machine. But oddly enough, this is what Node.js does, minus the first learn C part. So Node.js is the event model taken straight out of ePOL and writ large on the entire JavaScript community in the 21st century. And I think I go on this tangent on Node.js because I think Node.js success has a lot less to do with event loops or fast, so much as it does we can use JavaScript everywhere. And for that, Node.js folks are willing and prepared to put up with a lot. And so one of the things that they're prepared to put up with is auditing each bit of code they write or depend on to make sure that it doesn't block. And I think this is a good way to bring the discussion back to Go. Node.js and other evented models like Twisted and Java NIO, they're rooted in the idea of callbacks, right? So just like Windows 3.1 GUI programming. And if you can't, you get a notification, you're expected to process that as fast as possible. And if you can't, the responsibility for scheduling that work to happen later, hopefully in discrete increments, that's yours. That's your responsibility. And the penalty for failure is blocking and latency, and it's an unforgiving programming model, and it's inherent in the design of the I/O framework that you're given. So compare that to Java land. The serverlet model is hopelessly rooted in the idea of blocking. So I/O streams in Java do have a way of telling you how much data can be read before they block. But there's no way to wait for more data without the thread itself sleeping and periodically checking. And when you compose I/O operations with primitives like this, like think a gzip reader on top of a buffered reader on top of a network reader, it requires a thread per connection approach. So I explained before how threads and events are roughly comparable in terms of performance, and with 64-bit addresses spaces, the thread per connection is wasteful on paper, but in practice not that bad. So where's the clincher for Go? I think the Go routine argument starts by looking at the bigger picture. So it's not about doing efficient I/O. Sure, that's important. But what the Go routines do with that I/O. The difference between Nginx and the Tomcat examples, and the reason why Nginx, that evented web proxy, is successful in its niche is HTTP proxying is almost functional in its operation. Every request arrives independent of anything else. It's filtered, it's processed, and it's responded to without interaction by any other request. And that's why PHP remains so successful. So all that cruft about sessions and cookies and memcache and databases is the domain of the application server, and it's why threads seem to be the dominant paradigm here. They have complex state, not just a fixed state machine. So essentially, you can make the argument that applications are the nexus for state management, and that means coordination. So in Node.js, there is no coordination because there is no parallelism. At any one time, the active function can mutate whatever it needs. And this is basically how callback paradigm works. The whole program is this rolling gerbil wheel of leaving notes about work to do later. And in threaded application servers who must be threaded because of their I/O paradigms, coordination occurs between threads. So that means using the thread coordination primitives. So if your thread wants to take a lock but can't, and the thread has to register its interest in that lock, which is a syscall, and then go to sleep, that's another syscall. That's really going to be hurting on your performance, and especially if that performance is going to have to scale out. So it's not that having 10 to the 6 threads is a problem in itself, but the coordination between the 10 to the 6 threads is where the overheads reveal themselves. Syscall impact. Gosh, 1980s, 8-bit. So I kind of banged on a little bit about events and threads, and basically wanted to say why Go routine is the best of both worlds. I want to move on to the second technical thing that I think makes it really good, or Go for a 21st century programming language, distributed systems. So the success from Go is that it is the first language, or at least it certainly started a trend to produce programs that ran without a runtime. And that's not without its drawbacks, but I think the ability to compile or cross-compile as a program as a single static binary has unlocked So many deployment and usage scenarios that were thought too hard or too taxing since the 90s. And I put this little box over there because so much of the stuff that you're going to attend today and tomorrow and the day after is going to be about this box. And I don't want to bang on about that because you get to know about that. But just know that having a single static binary can reduce the complexity where everything else exists. So that's the distributed systems part. And that's certainly an incomplete answer because containers have basically probably put operating system vendors and distro packages out of business, or they will in the next decade. So the next and the third of the 5 is this garbage collection, bounded pause time for GCs, which is crucial for real-time servers. So from everything that I've researched about Go in my why Go? And what I think makes it 21st century with the garbage collection is this idea of memory management. So GC design in Go is aimed at reducing tail latency. Tail latency is the thing that blows up distributed systems, right? It's not running out of CPU. That's not the thing that blows it up. It's tail latency. Because a machine being slow to respond to a request, so triggering a retry storm due to garbage collection, it's no different than slow to respond because it's overloaded. However, monitoring and understanding the latter, CPU overload, is almost second nature to every programmer. So it's these 99 percentile latencies that just come and blow up your application and leave no trace that they're there. And I'm pretty sure that this is what all the SREs inside Google have been focused on for a decade because unpredictable tail latency directly translates to underutilization and wasted resources. So I look at the work that the primary engineers working on the GC, their names are Rick Hudson and Austin Clements, what they're doing outside of the Google sphere of their experience from their decades running huge 10 to the 7 machine workloads. So let's talk about the next one. We talked about threads and events, Go routines. We talked about distributed systems. We talked about garbage collection. We'll talk about the next one, which is still a little bit about garbage collection, but is more specific to memory locality. Memory locality, in my opinion, is way more important than it was when Java invented it over 20 years ago. Because when Java was an interpreted language, the cost of an object reference was immaterial, right? So I look at two of these things. How does the GC performance of Go compare to something like Java or the Hotspot Jvm? And these approaches are difficult to compare in garbage collectors because Java offers a selection of garbage collectors. And overall, the Java collectors, they're very mature and they're sophisticated and they've been tuned over the years. So in principle, they're excellent. I'm not going to argue that. But the downside is that the Java language itself puts a lot of stress on the GC. The biggest problem is that Java offers no value pointers, value types beyond the built-in int and double. So everything else has to be allocated as a separate object and then pointed to via references. And then the GC has to trace all these references, which takes time. And while the collection of the youngest generation in Java is extremely fast, a global garbage collection can take quite some time. So you have these specialized JVE engineers that make their living on this very niche area to tune things to make up for memory locality. Go, on the other side, has structs, which are inseparable from their types as values. So true value types. And the memory layout is much easier for the GC. So Go always performs full GCs, but mostly running in parallel with the application. Up until last year, I think, the GC cycle only required a stop the world phase. They got rid of that. Yeah, and 1.8, right? Yeah. So it's been removed in versions Go 1.8 and beyond. So all of these numbers and things that I talk about, it does, yes, depend a lot on what your application is doing, but overall, Go seems to be doing very well with its newest iteration of the GC. So another problem of Java in memory locality is the inability to return multiple values. So for that one, it often creates a wrapper object to hold the results. And the JVM can recognize this pattern and stack allocate the wrapper objects, but it doesn't happen without always putting increasing GC pressure in JVM. So the lack of the custom value types has ramifications not only for the garbage collection, but also for cache behavior. because that's why there's serious work on custom value types for Java for anybody that follows that, and that's going to be the major feature that's going to be planned for Java 10. I specifically mentioned the Hotspot Jvm because Robert Griesemer, one of Go's creators, helped to build the Java Hotspot virtual machine, which was built on technologies from implementations of the programming language Smalltalk named Strongtalk, and he was working on at the time. So again, we have this individual who was one of the architects of who now maybe has a hindsight, like 2020, of the things that he wishes he could do differently. Or that old adage, if you only knew now what you knew then, or if you only knew then what you knew now, right? So this comes to another famous quote about the making of Go, and I just wanted to segue briefly into this before I finish memory locality and what would, in terms of what would get added to the language and what would not. And this is from Ken Thompson. When the three of us, which is Ken and Rob and Robert, got started, it was just pure research. And just, we all got together and we decided that we hated C++. And returning to Go, we started off with the idea that all three of us had to be talked into every feature of the language. So there was no extraneous garbage put into the language for any reason. So it's not because they didn't do it because they couldn't. It's because they made a conscious choice not to. And I just wanted to take that. Let's go back to memory locality. Let's look at compact object layout for Go. So there's little control of how Java allocates its objects in memory. And with C++ you can, but then there are drawbacks, like requiring lots of value copying. But the other thing about Go is that there's no object headers. And that's important, again, for memory locality and for performance. Struct fields are not indirect. In Java, if object A has an instance of object B, then that's 2 memory allocations, and then worse locality. And so there's finer control over memory allocation in Go. And this is a small, but I think an important thing. Go uses UTF-8 because the creators of UTF-8 also are the creators of Go. But I should mention that UTF-16 uses twice the space, at least on Linux, and it requires transcoding when reading and writing. And I think that's a good case to demonstrate the sanity of UTF-8 as a string encoding. It makes sense to at least point to when Go programmers never have to ask, what encoding is this in? And if you've programmed in at least C++ or other languages, you've had to at least ask that question once. So what else? Lazy initialization of collections. So the 0 value of a map or slice in Go is an empty collection. It's not a nil pointer exception waiting to happen. So by contrast, Java positively encourages you to allocate empty collections that you're never going to use. Cliff Click has a good talk. He's a hardware researcher, and he has a good talk about how modern CPUs are basically memory bound, and like how all the cool things like speculative execution and branch prediction are all aimed at queuing up the next cache miss sooner. And so the processor and memory gap and cache size is limited by the speed of light. So expecting memory to get faster or cache size to be a function of dollars spent, it's fiction. So to map up memory locality, I hope that this gives you some technical points about how Go gives programmers the tools to talk about memory efficiently if they need, but only if they need, because it's also flexible. Because when that level of control is not required, it's not an all or nothing thing like in C++ or in Rust. So the last thing I want to talk about for a feature of Go as a language for the 21st century is this emphasis on readability. Large organizations have to hire inexperienced people. And I love this Brian Kernighan quote. Debugging is twice as hard writing the code as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it. And that's a pretty smart guy saying that, right? The other thing about readability is that code is read way more than it's written. Hundreds of times more than it's ever going to be written. It's written once and then it's read over and over and over again. So Go simple syntax brings out a lot of opinions, but let's again look at what's happening at Google around 2007, okay? Google as a company was started in 1999. By 2007, at the time when Go was released, it had almost 17,000 employees. 88% of those were engineers. And that was only the beginning. Here's where the numbers would be by 2010. 24,000. And here's where the numbers are today. Sorry, that says 2010. It's a typo, 2017. But today, Google has, by the end of 2017, it has almost 76,000 engineers. And the majority of these people, employees, but the majority of these employees, it's now hovering between 80 and 85%, they're software engineers. So if you write code with polymorphism and meta classes, imagine needing to debug that code, maintain that code, having to ramp up to growing that code base, which is growing by millions of lines every few months. There are several points that I want to make about this context with readability. And the first is about simplicity. Simplicity is a topic that can be very context sensitive. I've seen simple is better be taken very positively. I think everyone in the screen would agree. But I've also seen that people's retort when it's talking about Go is that it's an insult to intelligent programmers, or you're trying to commodify programming and create a situation where our bosses can replace us at will. And there's probably a whole lot going on with these statements. It could be culturally specific or interpersonal issues, but it's not an uncommon retort when you are in the Go community. So there's this set of programmers who feel intellectually offended that learning Go does not simultaneously mark them as the apex programmer the way that C++ does. I think the best way I've seen it is like undignified simplicity. So in talking with Dave Cheney, my fellow time traveler, in preparation for this talk, I was like, Dave, I've got some thoughts, and you want to see my thoughts? And Dave was like, I've got thoughts on your thoughts. I was like, I'm going to use those thoughts. So this is Dave talking from here on out. You'll hear Dave talk this afternoon too. But when I talked with Dave about readability, he gave me the following thoughts. You're not paid to program. You're not even paid to maintain somebody else's program. Really, essentially, you're paid to deliver solutions for the business that you work for, right? And I think that this argument is very successful with people who agree that their careers are benefited by delivering solutions, not by the lines of code that they write. And there are two more points about this, Dave's argument about like solutions, not code. And I think this is brilliant. And I can't even take credit. It's all Dave. So the first point is that programs which can't be maintained are going to be rewritten. Right? But that's mainly an argument for the pro-Go advocacy crowd, because if you want to have a career in Go, write programs that can be maintained. The second point is about mobility, right? Most of the people here will be looking at programming as a career, or have been programming and it's been your career. And a very shrewd quote about promotion and mobility: if you can't be replaced, you cannot be promoted. If your clever code is so integral to the company that you can never risk being taken off of that project, then sure, maybe you're never going to get fired, but you're also never going to be considered for a different project or be considered for promotion. And so if one day you do want to move sideways or up or whatever within your company without having to leave, you need to make sure that somebody else can do your job. And being able to maintain a piece of software starts with being able to read it. So turnover and company switching for engineers averages in 2017 and over the last decade, 18 to 24 months. So the only guarantee in your company, including you, is that you're going to leave. And this is the reality of working in software engineering in the 21st century. So in the last 10 years, if you've been in this business for 10 years, the average number of jobs and companies that we've been at maybe is going to be about 5. For some, it's even 10. And Dave further talked about his experience about having worked in Go across 4 organizations during our talk, and about maintaining other people's code, and also knowing I'm going to write code that I know is going to be maintained, that I have to leave and others are going to have to maintain. So this turnover and company switching for engineers, it's the reality of working in software engineering in the 21st century. And this is the context that matters beyond the programming language itself. Okay, So we've talked about context and people and some technical limitations that were happening in software and hardware around the time that Go was invented. But I think to drive things home, we really need to understand to understand software engineering, right? And I'd like to finish this talk about that. The larger picture at Google and the larger picture of our industry and how this is influencing the design of Go by taking this holistic view of things. The first is that how we define software engineering itself in 2017. And what is the difference? If I were to put it to you to define for me, what is the difference between software engineering and programming? It's a good question, right? And why do we have two words for these concepts? Aren't they one and the same? But the best definition that I've found is Titus Winters, who maintains the C++ libraries at Google, had standardized all the C++ dialects at Google. So I think he has something quite interesting to say about it. And his thing was, software engineering is different from programming because it's programming integrated over time. So it's a programming task is like, hey, I got my thing to work, right? And that's hard. But sometimes the right answer to a problem is, I'm going to write a program to solve this and just be done with it. But that's programming. Engineering is what happens when things need to live longer and the influence of time starts creeping in, right? And if you've worked in this industry for a long time, you understand that, right? Library versions get updated. The operating system gets deprecated. The language gets revised. The requirements have changed. You have to ship new features now. Other developers are working on the code base, changing services to have different options after a couple years. Rollouts, updating new servers, updating front ends, complex networks of servers. They're now in the millions, not just at Google, but at other tech behemoths, right? What else? I just listed a bunch here because I started getting excited about the idea of engineering over time. But moving to a new team. We already talked about moving to a new company. Moving to a new computer. Your hard drive dies. I mean, this happens. Time happens. Things change. And so how you handle that and how you keep your program working is engineering. That is what it is. And it may bleed into the programming itself. I think that was the thing that Titus said. But it could also be layered on top. And all this complexity is fundamentally a different flavor than programming. And it's different than I got it working. And sometimes it's not needed. But we don't, especially when we don't need to plan for the future. But when you aren't certain and about time, when you have to be prepared, this is software engineering and designing a language for software engineering, the impact of time on a system. So the point is, something that makes sense on the face of it in our everyday programming turns out to be a horrible idea when you start to think about change over time. And there are many things that do make a perfect sense in this limited domain. And sometimes we do work in a limited domain, but like in our programming domain. But they don't make sense when we're thinking about it as engineering and thinking about change over time. And I'll share the links, and I want you to go look at this talk because I think it blew me away. At the core, everything that we think about in software engineering is kind of time-based, right? So think about this. Version control. You go back in time to coordinate with your colleagues over time. Continuous integration. Making sure recent changes haven't broken the system. Unit tests, making sure your feature that you wrote won't be broken in the future. Refactoring, update something from the previous time to the present time. Design patterns, ability to plan for future changes without knowing what these changes are going to be. And then, of course, dependency management. So packages, which is the Go parlance of libraries, and those that we depend upon are going to change. So Go's holistic approach absolutely understands this about software engineering. And probably it reflects the zeitgeist that informed the original design of Go, specifically the focus on sustaining engineering through readability. So the continuance of many different engineers over a long period of time, these very clear module boundaries, aimed at keeping import dependencies between packages linear, thus keeping compile times down, is everything that I think was on the minds of the three creators of Go. So I'd like to close with talking about one last thing, which I call simplicity and the greater good. Simplicity, again, as I said before, it's often seen negatively, but in the context of order, sustainability, group cohesion, it's a benefit. And it's imperative that in some aspects of the organization, simplicity needs to be enforced. Oops. An example is road signs and road rules. The number of vehicular deaths when cars were first mass-produced after Ford introduced the industrial line relative to the population was extremely high. And authorities and government officials had to figure out how to fix these fatalities because cars, we weren't going to put people back in horses and buggies. So they started to come up with these rules. They started to impose limits, rules that everyone had to follow, right? So in the US, you have to drive on the right side of the road. You have to stop at the red light. You have to go at green. You have to follow the speed limit. You have to yield. And imagine if someone, in the name of imposition of freedom or creativity or my rights, decided that they just wanted to drive on the left side of the road, like they do in the UK. They would probably cause damage and maybe even kill people. Lives would get lost. So there are systems sometimes when imposing limits can afford us all the ability to use it efficiently and also safely. And imposing limits like this makes things possible. And it's exactly what Go did, right? And it lets you evolve to the place or the point where anything that needs to be changed can be changed. This is sustainability. And if you feel like this is very top-down, you're right. Because Go is first and foremost a language meant for this context. Rob Pike says Go is not an academic language. It's meant to be used in a big crowded place with 76,000 engineers in 2017 where digital traffic laws and street signs are needed. So I give you this quote, which, gosh, am I like a real programmer now that I'm using Dijkstra? Simplicity is a great, I think everyone has probably heard this, and I think you could, say it every morning to yourself as your mantra. Simplicity is a great virtue, but it requires hard work to achieve and education to appreciate. And to make matters worse, complexity sells better. So Go doesn't have a lot of things in the language, as you saw before, but simplicity is ultimately reductive. You can't add more things to make things more simple, right? You can't add wrappers and super wrappers and libraries. There's got to be a point where you do a redo and you purposely decide to make it small. So if someone had come up with Go 20 years ago, it wouldn't have survived, nor would it have been adopted. There is no pretense that Go is going to be the end-all be-all. But for a pretty big set of the problems that we needed to solve today, it does a good job. And these are the problems that weren't there 20 years ago, nor are they going to be there in 20 years from now. And this is the reason why Go is popular today. These are the conditions that make Go useful. So, given what I've told you, my challenge to you is to watch these conditions for today and see them change, because it will allow you to predict the ascent of the next new things. And that may surprise you. Thank you.